Hello everybody and welcome back to our course. So after we have coded our sticker album challenge with the Python standard library, we now start to code in a vectorized manner with the NumPy package. And our target is to boost our performance and to have a much faster code than before. And by doing so, we can answer more advanced and more complex questions. So for example, if and to what extent trading and exchanging duplicates with others is helpful and beneficial, and many more questions. Vectorized coding with NumPy typically is not only much faster, but also the code itself is shorter and with fewer lines of code, because typically we don't have structures like nested for loops and if statements and so on. However, this comes at a cost. So if you are not used to vectorized code, it's less intuitive and it might be harder to read and to understand. And sometimes vectorized NumPy code is like the Egg of Columbus, so it's very hard to come up with the solution. But once you have got it, it seems pretty easy and straightforward. But I think you will see later what I mean here. Alright, so let's start importing NumPy with import NumPy as NP, and we also import matplotlib and use the Seaborn style. And then we start with one simulation, and before we go to our sticker album challenge, I want to introduce a toy example where I think the idea behind the code gets clearer and more intuitive. So we want to roll the dice, and of course we assume that we have a standard dice with 6 pages, and we are throwing the dice 6 times, and we want to count the unique numbers we get. So first of all we have the variable dice pages, it's 6, and the number of throws is also 6. And then we set the random seed to 42. So a NumPy random numbers generator with the same seed as the random generator in Python standard library, so they are not returning the same numbers even if they have the same seed. So it's important to know here actually. And then we are creating random integers in range 1 inclusive until 7 exclusive. So here the ending point is exclusive. That's why we have here dice pages plus 1, 7. And the number of random integers, so throws is 6. And this is kind of a vector, and we assign the variable v. So now we have a NumPy array with 6 elements, 4, 5, 3, 5, 5, 2. And there's the NumPy function npUnique. This sounds very much what we need, and where we pass our array v to npUnique. And there we can see, so we have here the 5 is a duplicate. So we have 2, 3, 4, 5 as unique numbers. And we can also count the length of our unique array by applying the length function. So there we are actually counting the number of unique values. It's 4. So this is exactly what we need, and it should also work with many simulations. So to say in a two-dimensional structure on a matrix, so what do I mean with a two-dimensional structure? So let's assume we repeat the process of throwing the dice 6 times, let's say 10 times, so we have 10 simulations or repetitions. And we can actually create 10 times 6 random integers, so we again use np_random.randint. And create 10 times 6 random integers in the range between 1 and 6 inclusive, and then we reshape the matrix to 10 rows and 6 columns. So we have 10 rows, which are the simulations, and in each simulation we are rolling the dice 6 times, so we have 6 numbers, and we assign the variable m for matrix. So there you can see here we have a matrix with 10 rows, which are our simulations, and 6 columns. And let's have a look at the first row. So we have here our first simulation where we get with the roll of the dice 6 times, we get 4, 5, 3, 5, 5, 2. And then actually npUnique should get us for each row the unique values actually, and we try this. NP-unique returns us the unique values in the whole matrix, and yeah, there's actually no way that NP-unique returns us 10 times actually an array with the unique values in each row. So NP-unique does actually not work with many simulations, and that's the reason why we have to find an alternative solution. And we start again with one simulation. So we simulate the vector v, and we will then sort the vector v. So let's see what we get. So here we have our sorted vector in ascending order, so 2, 3, 4, 5, 5, 5. And what we are doing now, we are creating two slices of our array v. So the first slice is from the element at the position 1 until the very last element. So actually we are dropping the very first element. And we are creating a second slice of v, where we start with the very first element until the very last element, but excluding the very last element. So we are actually dropping here the 5, and for this array we are dropping the 2. And what we are now doing, we are checking element-wise if the respective elements of the two arrays are equal or not. And if they are not equal, we count 1, and if they are equal, we count 0. And then we add up all ones. And in the end, we are adding one more because the first and the last element that we dropped, so the 2 and the 5, they are also not equal. So we have to count another time. So let's do this. We compare 2 and 3. It's not equal. We count 1. We compare 4 and 3. That's not equal. We count 2. We compare 5 and 4. That's not equal. We count 3. And 5 and 5, and 5 and 5 is equal, so we have 3, and additionally we count another one, so we have 4. So in the NumPy code, this is the correct expression here. So we are element-wise comparing the elements of the first slice with the element of the second slice if they are unequal. And now we should get an array with booleans. So we get true, 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 false, false. So that's actually what we did before here. So true, 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 false, false. And then we can count the number of unique values by summing up here the array. So true stands for 1, false for 0. So the sum of the array should give us 3. And we add another one. So then we should get for unique 4, and this is actually correct. So, and we can also increase the amounts of throws and check this one more time if it works. So we again produce random integers between 1 and 6, and we do that 12 times and get a sorted vector v. Then we make the two slices and element-wise compare the two slices if they are not equal. So we get here true, false, 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 true, false, true, false, false, false. And yeah, we can check this also manually. So we have here a true, then a false, then a false, 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 true, false, true, and 3 times false. And now if we want to count the number of unique values, we can take the sum over the Boolean array and add another one. And we also get 4, and 4 is correct actually if we see here at the original array. So we have a 2, we have 3, we have 4, and we have 5, so 4 unique values. Alright, so now we can turn to our sticker album challenge, and we set our album capacity to 600 and the purchase stickers to 800 and set the seed to 1 to 3. And now we create random integers between 1 and 600 including, and we create 800 random integers. And we can check the shape of our vector, so we get 800 random integers, and we can sort it. So let's check here our vector. So we get 2 times 1, 2 times 2, 3, 4, and so on. And now we can count the number of unique stickers or unique values in our vector v. So we make the slices, compare them if they are unequal, take the sum over the Boolean array and add another one. And this results in 439 unique values or unique stickers. And alternatively, we can transform our vector into a set. So the set object removes all duplicates and can count the length of the set. And this should give us, hopefully the same result. And that's true. Alright, so far we have now created a vectorized code for one simulation. And in the next session we will continue to build and transform our code into a matrix form where we can actually also apply many simulations. So hope to see you there.